During Tesla AI Day, Andrej Karpathy, Director of AI and Autopilot Vision at Tesla, went into a great deal of detail about how and why Tesla engineers have expended massive effort to transform video images from Tesla cameras into an abstracted vector space. The way they achieved this and the results are astounding. So let's take a look. For those of you interested in investing, check out WeBull, an amazing platform for buying and selling stocks, and now cryptocurrencies like Bitcoin, Dogecoin, and others. Open an account and get a free stock valued at up to $200, and fund your account and get another free stock valued at up to $1,600. Check out the link in the description and help the channel at the same time. Hey y'all, it's Dr. Know-It-All. First of all, this is episode 3 in Tesla's AI Day video series. I'm actually making a playlist out of that. You can catch the other ones up here, and I'll try to remember to put a link to the playlist in the description as well. Also, you'll notice I'm wearing the same TeslaBot t-shirt again. That wasn't really intentional. I wasn't going to wear the same, t-shirt 2 days in a row or 2 episodes in a row, but I realized that I'm going to talk about Transformers today. Transformers. Robots in disguise. So anyway, yeah, I just had to wear the TeslaBot shirt again. And of course, you can order this for yourself at our merch store, so definitely check out the link in the description. So first, let's start with a clip that walks down memory lane a little bit.
So the processing starts in the beginning when light hits our artificial retina, and we are going to process this information with neural networks. Now, I'm going to roughly organize this section chronologically. So starting off with some of the neural networks and what they looked like roughly 4 years ago when I joined the team, and how they have developed over time. So roughly 4 years ago, the car was mostly driving in a single lane going forward on the highway. And so it had to keep lane and it had to keep distance away from the car in front of us. And at that time, all of processing was only on individual image level. So a single image has to be analyzed by a neural net and make little pieces of the vector space, process that into little pieces of the vector space. So this processing took the following shape. We take a 1280 by 960 input, and this is 12-bit integers streaming in at roughly 36 hertz. Now we're going to process that with a neural network. So we instantiate a feature extractor backbone. In this case, we use residual neural networks. So we have a stem and a number of residual blocks connected in series. Now the specific class of ResNets that we use are RegNets, because RegNets offer a very nice design space for neural networks because they allow you to very nicely trade off latency and accuracy. Now these RegNets give us, as an output, a number of features at different resolutions and different scales. So in particular, on the very bottom of this feature hierarchy, we have very high resolution information with very low channel counts. And all the way at the top, we have low resolution spatially, but high channel counts. So on the bottom, we have a lot of neurons that are really scrutinizing the detail of the image. And on the top, we have neurons that can see most of the image and have a lot of that scene context.
So as you saw, Dr. Karpathy talks about historically, which was just a few years ago, everything was done in Tesla and most other full self-driving, etc., was all done in single image space. And they used RegNets to perform these tasks as they allow for a trade-off between latency and accuracy, which is really, really good for full self-driving, right? You don't need super accuracy in driving. You just need to be within a few centimeters of where you expect to be, but you really do need latency low. In other words, you have to be able to make decisions in real time. You can't just, sit around and say like, wait, give me about 5 seconds and I'll come up with the answer. It has to be done like, in real time. Anyway, RegNets are an extension of ResNets, which have been a standard, in neural networks since 2012. I'm not going to go into much detail about this because there's so much more to cover in this episode. But anyway, you can look into it more if you're interested.
So for example, we want to do traffic light recognition and detection, a lane prediction, and so on. So very quickly, we converge in this kind of an architectural layout where there's a common shared backbone and then branches off into a number of heads. So we call these, therefore, Hydranets, and these are the heads of the Hydra. Now, this architectural layout has a number of benefits. So number one, because of the feature sharing, we can amortize the forward pass inference in the car at test time. And so this is very efficient to run. Because if we had to have a backbone for every single task, that would be a lot of backbones in the car. Number two, this decouples all of the tasks, so we can individually work on every one task in isolation. And for example, we can uprev any of the data sets or change some of the architecture of the head and so on, and you are not impacting any of the other tasks. And so we don't have to revalidate all the other tasks, which can be expensive. And number three, because there's this bottleneck here in features, what we do fairly often is that we actually cache these features to disk. And when we are doing these fine-tuning workflows, we only fine-tune from from the cached features up and only fine-tune the heads. So most often in terms of our training workflows, we will do an end-to-end training run once in a while where we train everything jointly. Then we cache the features at the multi-scale feature level. And then we fine-tune off of that for a while. And then end-to-end train once again, and so on. So here's the kinds of predictions that we were obtaining, I would say several years ago now, from one of these Hydranets. So again, we are processing individual images. There we go. We are processing just individual image, and we're making a large number of predictions about these images.
As this clip shows, Andrej Karpathy talks about Hydranets, and I've talked about this pretty extensively in previous videos, which you can catch here explaining Andrej. So I'm not going to spend a lot of time here on that. They're very, very cool. You can see a lot of detail about that if you watch my other videos. But anyway, it allows Tesla to train on specific tasks and not have to rework, revalidate, retrain the entire network all the time. And what that means is that they can basically cache the general state of the network, the body, the trunk of the Hydranet, and then they can actually go in and train each of the heads of the Hydranet independently of each other, and then go back and retrain the whole thing once in a while. That just saves a ton of time because everybody's working independently, they're not messing with everybody else's stuff, and you don't have to retrain the whole network all the time because the whole network is huge. So this is all very good, it's very, very cool, but what are the problems? Number one, they're dealing with one image at a time, and number two, they're dealing with raster images or just pictures, you know, 8 pictures actually, 8 pictures at a time that are independent from each other. So as you might expect, the system started to break, and interestingly enough, Karpathy talks about how it first became very evident in smart summon in parking lots, which wouldn't be the obvious thing.
So where this first started to break was when we started to work on smart summon. Here I am showing some of the predictions of only the curb detection task, and I'm showing it now for every one of the cameras. So we'd like to wind our way around the parking lot to find the person who is summoning the car. Now the problem is that you can't just directly drive on image space predictions. You actually need to cast them out and form some kind of a vector space around you. So we attempted to do this using C++ and developed what we call the Occupancy Tracker at the time. So here we see that the curb detections from the images are being stitched up across camera scenes, camera boundaries, and over time. Now there were two major problems, I would say, with the setup. Number one, we very quickly discovered that tuning the occupancy tracker and all of its hyperparameters was extremely complicated. You don't want to do this explicitly by hand in C++. You want this to be inside a neural network and train that end to end. Number two, we very quickly discovered that the image space is not the correct output space. You don't want to make predictions in image space. You really want to make it directly in the vector space. So here's a way of illustrating the issue. So here I'm showing on the first row the predictions of our curbs and our lines in red and blue. And they look great in the image, but once you cast them out into the vector space, things start to look really terrible, and we are not going to be able to drive on this. So you see how the predictions are quite bad in vector space, and the reason for this fundamentally is because you need to have an extremely accurate depth per pixel in order to actually do this projection. And so you can imagine just how high of a bar it is to predict that depth so accurately in these tiny, in every single pixel of the image. And also, if there's any occluded area where you'd like to make predictions, you will not be able to because it's not an image space concept in that case. So we very quickly the other problems with this, by the way, is also for object detection. If you are only making predictions per camera, then sometimes you will encounter cases like this where a single car actually spans 5 of the 8 cameras. And so if you are making individual predictions, then no single camera sees all of the car. And so obviously you're not going to be able to do a very good job of predicting that whole car. And it's going to be incredibly difficult to fuse these measurements.
So first, just to recap for those who don't understand, what is the difference between raster and vector images? Well, a raster image is what you're used to, right? That's a JPEG image or a PNG image or a TIFF image or whatever it is. It is a bunch of pixels in a scene, right? So if you've got a picture of a dog, it's just a bunch of pixels with different colors, and that represents to our eyes a picture of a dog. Now, you can compare that to a vector representation, which is a mathematical 3-dimensional representation with both position and color texture information. So it'd be sort of like the difference between looking at a picture of a dog and looking at a real dog, right? A picture of a dog gives you a good deal of information, right? But it's from one angle, it's got one type of lighting, you can't really change anything, and that's what you get. Whereas a real dog, which is 3-dimensional, allows much more complex representation, including different angles as you move around, different lighting conditions, and of course, if you do it in video, you get motion as well. So, you know, a real real dog obviously gives you a great deal more information than a picture of a dog. So that's basically the difference between raster and vector. Now, of course, vector is not, real by any means. What it is a three-dimensional, or actually four-dimensional because it includes time. It's a 4D representation of objects in a tensor, which is just a four-dimensional matrix. So essentially what you've got is you've got a whole bunch of numbers that represent where something is in space, and then you've got a whole bunch of other numbers that represent what each of the colors are that are associated with all of those positions in space. So if you've done any kind of 3D animation work like I have, you are quite used to this idea where everything has a position and a color in space. And also, of course, a velocity if you're dealing with video sequences. So anyway, Karpathy et al. Tried originally to use C++ to sort of explicitly write all this stuff, which is yikes. So they tried to stitch all the scenes together and cast them into 3D space, using C++, hard coding it. It turns out that this is really, really hard to do. Tuning was exceptionally hard, and also image space is a bad output space. So they were kind of pre or sort of quasi-converting it into vector space, but they were reproducing it back into image space again. So what they realized they needed to do was to abstract everything just sort of permanently into vector space. And the representation of that, you can think of it as you go from looking out the window of your car to getting like a satellite down view of your car, right? Or a, Google Earth kind of thing, something like that. So you're going from seeing things like this to seeing things top down. That's what they needed to do. And they needed to abstract that, and they needed to go kind of permanently into that space to do everything else.
So we have this intuition that what we'd like to do instead is we'd like to take all of the images and simultaneously feed them into a single neural net and directly output in vector space. Now, this is very easily said, much more difficult to actually achieve. But roughly, we want to lay out a neural net in this way, where we process every single image with a backbone, and then we want to somehow fuse them. And we want to re-represent the features from image space features to directly some kind of a vector space features, and then go into the decoding of the head. Now, so there are two problems with this. Problem number one, how do you actually create the neural network components that do this transformation? And you have to make it differentiable so that end-to-end training is possible. And number two, if you want vector space predictions from your neural net, you need vector space data sets. So just labeling in images and so on is not going to get you there. You need vector space labels.
So as this clip talks about, Karpathy says that they took all of the images and they feed them into one neural network, which is hard to do. I think that's a massive understatement. It's not hard to do. It's really, really hard to do. But basically, they have that question mark, and I sort of thought about the South Park underwear gnomes.
You see, phase 1, collect underpants. Phase 2, phase 3, profit.
But essentially, they knew what they needed to do. They needed to get from here, the raster images, to a vector space representation, but they didn't quite understand how to do that. So they spent a great deal of time and engineering effort to get over that hump. And of course, as we'll talk about in a future episode, so make sure you're subscribed and you hit the bell notification icon, they also have to label all this data in vector space, not in image space. And that's a whole other can of worms that we're going to deal with in the future.
So here's the rough problem, right? We're trying to have this bird's eye view prediction instead of image space predictions.
So as you see here, the basic issue is that we want a bird's eye view, like a top-down 2D view, like your GPS, but we have to create this out of 2D, like sideways images, like a picture that you would take out the front of your car window. So of course, this is really, really hard to do, which is why LiDAR is very popular, right? LiDAR shoots out rays of visible light and bounces them back again. It's an easy cheat as it raycasts into the world to get depth, but it's also super brittle. It can be fooled very easily. It can be occluded easily. It causes sensor fusion issues, and it's just a really problematic technology. So ideally, what you want to do is convert from these sideways, front-facing 2D images to a top-down vector space 2D map. But of course, the question is, how do you do that? Which is why people use LiDAR, right? They're like, we have no idea how to do this, so we're just going to use LiDAR to cheat this. But Tesla said, hey, we can figure this out.
So for example, let's focus on a single pixel in the output space in yellow. And this pixel is trying to decide, am I part of a curb or not, as an example. And now, where should the support for this kind of a prediction come from in the image space? Well, we know roughly how the cameras are positioned and their extrinsics and intrinsics, so we can roughly project this point into the camera images, and the evidence for whether or not this is a curb may come from somewhere here in the images. The problem is that this projection is really hard to actually get correct because it is a function of the road surface. The road surface could be sloping up or sloping down, or also there could be other data-dependent issues. For example, there could be an occlusion due to a car. So if there's a car occluding this viewport, this part of the image, then actually you may want to pay attention to a different part of the image, not the part where it projects. And so because this is data dependent, it's really hard to have a fixed transformation for this component. So in order to solve this issue, we use a transformer to represent this space. And this transformer, it uses multi-headed self-attention and blocks of it. In this case, actually, we can get away with even a single block doing a lot of this work. And effectively what this does is you initialize a raster of the size of the output space that you would like, and you tile it with positional encodings with sines and coses in the output space. And then these get encoded with an MLP into a set of query vectors. And then all of the images and their features also emit their own keys and values, and then the query's keys and values feed into the multi-headed self-attention. And so effectively what's happening is that every single image piece is broadcasting in its key what is it a part of. So hey, I'm part of a pillar in roughly this location, and I'm seeing this kind of stuff, and that's in the key. And then every query is something along the lines of, hey, I'm a pixel in the output space at this position, and I'm looking for features of this type. Then the keys and the queries interact multiplicatively, and then the values get pooled accordingly. And so this re-represents the space, and we found this to be very effective for this transformation.
So as you heard in this clip, Tesla figured out how to roughly project into 3D space, but there were many problems with doing this. Number one is that camera alignment and distortion are not perfect, and number two is that occlusion of a camera can happen very easily because something can come in front of another object. So what's the solution? Transformers. Transformers are the cool new kid on the block when it comes to neural networks. They've only been around for about 4 years, and I can do an entire episode. In fact, I think I will do that if the interest is there. I think transformers are really, really worth talking about, but again, outside the scope of this particular video. But in very, very brief, transformers use multi-headed self-attention like LSTM networks, but they're more flexible in terms of their input-output needs. So like I said, they're very new, they're like 4 years old, but they have transformed neural networks, and in particular language modeling. But now Karpathy and people like him are beginning to use this in image work as well as in linguistic work. So transformers provide a very flexible architecture that can essentially learn anything, but they need massive high quality data to learn, and they can be extremely compute intensive both in the learning and in the deployment phases. In essence, what transformers are doing are they're creating dictionaries of space and features in this particular case, and it can be with words as well. But anyway, they're creating dictionaries of space and features that can be queried. And this is a rough description, of course, it's not accurate in detail, but we just need the basic understanding here. So anyway, what can happen is a camera can say, hey, I'm the left pillar camera, and at this pixel, I see a dog. Another part of the network can then ask, hey, do you see any dogs at this approximate location? And this camera network can answer that query. And in this case, it would be positive. It would say, yes, I do. But of course, as with engineering, always there are other problems involved.
So one more thing, you have to be careful with some of the details here when you are trying to get this to work. So in particular, all of our cars are slightly cockeyed in a slightly different way. And so if you're doing this transformation from image space to the output space, you really need to know what your camera calibration is. And you need to feed that in somehow into the neural net. And so you could definitely just like concatenate the camera calibrations of all of the images and somehow feed them in with an MLP. But actually, we found that we can do much better by transforming all of the images into a synthetic virtual camera using a special rectification transform. So this is what that would look like. We insert a new layer right above the image, rectification layer. It's a function of camera calibration, and it translates all of the images into a virtual common camera. So if you were to average up a lot of repeater images, for example, which face to the back, you would, without doing this, you would get a kind of a blur. But after doing the rectification transformation, you see that the back mirror gets really crisp. So once you do this, this improves the performance quite a bit.
So what Dr. Karpathy is talking about here is that they need to rectify or correct each camera view into a, kind of quasi-perfect virtual camera. And this allows the camera views to be stitched together. So essentially every camera lens has kind of distortion, and of course there's also visual distortion and there's blurring and stuff like that. And they go through stages to get rid of all of that stuff and turn them into kind of perfect camera views that they can then stitch together very efficiently. Now, I say this like, oh yeah, that's so easy to think about, but it's really, really difficult. But like I said, Tesla eats difficult for breakfast. But anyway, when you do this, voila, look at the improvement in casting.
So here are some of the results. So on the left, we are seeing what we had before, and on the right, we're now seeing significantly improved predictions coming directly out of the neural net. This is a multi-camera network predicting directly in vector space, and you can see that it's basically night and day. You can actually drive on this. And this took some time and some engineering and incredible work from the AI team to actually get this to work and deploy and make it efficient in the car.
I think it's really funny that he said some time and some engineering went into this. I mean, again, talk about understatement. But anyway, making it efficient in a car is incredibly difficult to do. You have to be so sensitive to latency at all times, right? Again, you can't have it making a decision and saying, just give me 2 seconds to make this decision. It's got to be making the decision multiple times a second. So latency is super crucial. But anyway, that's all engineering stuff.
This also improved a lot of our object detection. So for example, here in this video, I'm showing single camera predictions in orange and multi-camera predictions in blue. And basically, if you can't predict these cars if you are only seeing a tiny sliver of a car. So your detections are not going to be very good, and their positions are not going to be good. But a multi-camera network does not have an issue. Here's another video from a more nominal sort of situation. And we see that as these cars in this tight space cross camera boundaries, there's a lot of jank that enters into the predictions. And basically, the whole setup just doesn't make sense, especially for very large vehicles like this one. And we can see that the multi-camera networks struggle significantly less with these kinds of predictions. Okay, so at this point, we have multi-camera networks, and they're giving predictions directly in vector space.
But anyway, what you can see from this is how much better the blue images are than the orange images. So the red image is the ego car, and it's projecting out, and the orange images are the old version of it, and you can see how they're all distorted and not in the right place, and the blue images are significantly better in terms of obstacles that it has to deal with. So that makes it work for space, but what about time?
But we are still operating at every single instant in time completely independently. So very quickly, we discovered that there's a large number of predictions we want to make that actually require the video context, and we need to somehow figure out how to feed this into the net. So in particular, is this car parked or not? Is it moving? How fast is it moving? Is it still there, even though it's temporarily occluded? Or for example, if I'm trying to predict the road geometry ahead, it's very helpful to know if the signs or the road markings that I saw 50 meters ago. So we try to develop, we try to insert video modules into our neural network architecture, and this is kind of one of the solutions that we've converged on. So we have the multi-scale features, as we had them from before, and what we are going to now insert is a feature queue module that is going to cache some of these features over time, and then a video module that is going to fuse this information temporally. And then we're going to continue into the heads that do the decoding. Now, I'm going to go into both of these blocks one by one. Also, in addition, notice here that we are also feeding in the kinematics. This is basically the velocity and the acceleration that's telling us about how the car is moving. So not only are we going to keep track of what we're seeing from all the cameras, but also how the car has traveled.
When Dr. Karpathy here talked about lack of memory, what he means is that each frame basically forgets what just happened before it, right? So imagine if you were driving and you kept forgetting everything you saw every, half a second or something like that. It would be extremely difficult to drive because you depend on that memory, right? You're like, oh, there was a car behind me, so I need to check in my blind spot before I turn into another lane because that guy might have passed me by now, right? So you need that memory to be able to keep track of what you're doing. So what we need to do is we need to stitch our cameras together for object detection, and we need to stitch the images together into video sequences. In other words, is a car parked or is it moving? You're right, you need memory for that. Is something that's occluded going to reappear again in just a second, etc., etc. So the basic technique here is to place a feature queue module plus a video module in before the multi-camera feature output. You'll note that this is happening fairly late in the process. You can see that from the image. And at this point, we've traded resolution, which is the original pixel count, for feature channel depth, which is the 20 by 80 part. In other words, 20 by 80, if you imagine that as pixels, is a very, very small, quote, image, but it has 256 filters or channels associated with it, and it has a 60 frame queue. So at 36 hertz, that's about 1.67 seconds worth of memory. So of course, 1.67 seconds is not great for really long-term planning, but it's way better than instantaneous. And if you haven't caught that, you can see my plan ahead video up here, and we're gonna talk about that because I actually referred to that at AI Day also, but we don't have time for that in this particular video. But anyway, so there's different things. But what they have is they have sort of in their main queue for driving, they have about 1.5 seconds of memory. And then of course, after the feature queue, they convert that to a video or moving sequence or 4D space. And if you're interested in that, you can actually see a video I did last year on this that Elon Musk commented on. So anyway, the videos are about 1.67 second clips. And video here is not what we would recognize as video. It's a vector feature space video, not something we would ever see ourselves looking out the window. But of course, this is much, much more useful. That's why they're going through all of this effort to get there. So they can remember features for about a second and a half. They can do video-based feature detection, and they can act on this sequence now. And you can also see that they're plugging in kinematics of your car as input too, which is very important, right? You need to know how fast and what direction you're moving, or are you going uphill or downhill, etc. In other words, if you're still, you don't really care about a car that's 5 meters ahead of you, but if you're doing 100 kilometers an hour, you better be very aware of and care about a car that's only 5 meters away from you. Now let's take a look at an example and see how this works.
So here's a cartoon diagram illustrating some of the challenges here. There's going to be the ego car is coming from the bottom and coming up to this intersection here, and then traffic is going to start crossing in front of us, and it's going to temporarily start occluding some of the cars ahead. And then we're going to be stuck at this intersection for a while and just waiting our turn. This is something that happens all the time and is a cartoon representation of some of the challenges here. So number one, with respect to the feature queue and when we want to push into a queue, obviously we'd like to have some kind of a time-based queue where, for example, we enter features into the queue, say, every 27 milliseconds. And so if a car gets temporarily occluded, then the neural network now has the power to look and reference the memory in time and learn the association that, hey, even though this thing looks occluded right now, there's a record of it in my previous features, and I can use this to still make a detection. So that's kind of like the more obvious one, but the one that we also discovered is necessary in our case is, for example, suppose you're trying to make predictions about the road surface and the road geometry ahead, and you're trying to predict that I'm in a turning lane, and the lane next to us is going straight. Then it's really necessary to know about the line markings and the signs, and sometimes they occur a long time ago. And so if you only have a time-based queue, you may forget the features while you're waiting at your red light. So in addition to a time-based queue, we also have a space-based queue. So we push every time the car travels a certain fixed distance. So some of these details actually can matter quite a bit. And so in this case, we have a time-based queue and a space-based queue to cache our features, and that continues into the video module.
So as Dr. Karpathy talks about, they push to the queue every 27 milliseconds, which is very fast for us humans, but it's an eternity for computers. And this allows memory of objects that are occluded by other objects, for example, cars that blind you to the car across the street, but also cars need to remember things spatially. In other words, they need to remember things like lane markings. This is not obvious, but it's very important to the way we drive. In other words, we not only need a time-based queue, we need a space-based queue. So in other words, if you sit for a long time, like a few seconds, the car is going to forget what it was there for, right? It's like, oh, I've only got 2 seconds of memory, so it's auto dementia, I guess. But anyway, you can push to the queue based on position. In other words, every meter forward you push to the queue, as well as time, which would be every 27 milliseconds. So you've got two different queues going on here. The space-based queue will stick around if you're sitting still until you start driving again. So that gives you memory when you're stopped. And then how is this all put into video? Well, a spatial RNN, which is super cool. I had never seen one of these before.
But the one that we actually like quite a bit as well, and I want to spend some time on, is a spatial recurrent neural network video module. And so what we're doing here is, because of the structure of the problem, we're driving on two-dimensional surfaces. We can actually organize the hidden state into a two-dimensional lattice. And then as the car is driving around, we update only the parts that are near the car and where the car has visibility. So as the car is driving around, we are using the kinematics to integrate the position of the car in the hidden features grid. And we are only updating the RNN at the points where we have that are nearby us, sort of.
So let's think about spatial RNNs, or recurrent neural networks, for video. The hidden state is for space, not time here. So, historically RNNs are all about time-based cues. They're series prediction things. But what you're doing is you're doing it in space instead of time. So you only need to update the model for near distance elements, and you can save a ton of compute by not updating far away elements that don't really matter right now. So in the end, what do we get out of all of this? Well, we get beautiful videos, but more importantly, we get extremely information-rich videos. Again, these are videos in feature space, not in image space.
Here, what I'm going to show you is the car driving around, and we're looking at the hidden state of this RNN, and these are different channels in the hidden state. So you can see that this is after optimization and training this neural net. You can see that some of the channels are keeping track of different aspects of the road, like, for example, the centers of the road, the edges, the lines, the road surface, and so on. Here's another cool video of this. So this is looking at the mean of the first 10 channels in the hidden state for different traversals of different intersections. And all I want you to see basically is that there's cool activity as the recurrent neural network is keeping track of what's happening at any point in time. And you can imagine that we've now given the power to the neural network to actually selectively read and write to this memory. So for example, if there's a car right next to us and is occluding some parts of the road, then now the network has the ability to not write to those locations. But when the car goes away and we have a really good view, then the recurrent neural net can say, okay, we have very clear visibility. We definitely want to write information about what's in that part of space.
So each of these little videos that Dr. Karpathy showed are different filters or channels, and each keeps track of different parts of the road, like different road features, like the center, the edges, the lines, the lane markings, all in one output space. And then all of these are merged in the end to make predictions. So for anybody who knows about neural networks, this is just like how neural networks work in general. They reduce original image dimensions into filters or channels that have features that they care about and act on. But here we're doing this in vector space instead of image space, and there's been so much to get to this stage, so much engineering effort and work. So Tesla is doing a ton of pre-processing to get to this more abstract feature space that is a vector space. But the benefits are that now you can drive in that space. One fascinating thing is that Dr. Karpathy talks about how the RNN can ignore areas that are occluded until they're not anymore. And this is just mind-blowingly cool, right? So what they do is they say, like, I can't see this stuff, it's occluded, so just ignore it right now and don't update it. But when it's not occluded anymore, yeah, you can update it then. So these RNNs now have spatial in addition to temporal attention, which is a paradigm shift. It's a series data, but it's spatio-temporal series rather than just temporal. And finally, let's look at a few more image sequences that show how the ego car builds the road network around it to drive on in real time. And again, compare this to LiDAR systems that have to have this map built for them by a mapping car. And think of all the things that are constantly changing. But the Tesla car is doing this all in real time.
Here's a few predictions that show what this looks like. So here we are making predictions about the road boundaries in red, intersection areas in blue, road centers, and so on. So we're only showing a few of the predictions here just to keep the visualization clean. And yeah, this is done by the spatial RNN. And this is only showing a single clip, a single traversal, but you can imagine there could be multiple trips through here, and basically a number of cars, a number of clips could be collaborating to build this map, basically and effectively an HD map, except it's not in a space of explicit items, it's in a space of features of a recurrent neural network, which is kind of cool. I haven't seen that before.
So as you can see, the car itself is building the road in real time, which is extremely flexible and powerful, and you can leverage the fleet. In other words, the more times this road is traversed either by you or by other cars, the better these maps get. For example, if a truck is to your right as you drive this intersection the first time, the right-hand view is occluded. But if another car or you later redrive this route and there's no truck there, right, you can see that same area and you can fill it in. So the feature space map can improve each time the area is driven, which means the fleet can learn and get better and better at driving common roads, which is like... So in short, all of this is really, really hard to do, which is why nobody else has ever done it. The amount of engineering and brain power shown here is truly humbling in scope, but it's utterly critical to actually getting full self-driving to work on any platform, and it does many, many things that LiDAR simply has no way of doing. Recognizing lane markings, reading signs, dealing with occlusions, spatio-temporal memory, or in other words, remembering in both space and time, and you can get your fleet to improve these feature space representations each time they drive the same roads. Other car autopilot systems just can't compete with the power and flexibility of this architecture. All of this means Tesla full self-driving is going to get more and more human in its driving ability, and it will eventually, probably soon, exceed our abilities. And I welcome that, as I'd love to let my car chauffeur me to work today. All right, I hope you enjoyed this episode and found it fun and informative and, kind of mind-blowing. We still have to deal with data and hardware, so definitely subscribe and hit the bell notification icon to be sure you can catch those episodes. As always, a huge shout out to my patrons on Patreon. We actually have several new patrons that have signed up very, very recently. I will give you all a shout out in the next episode. I just, I have work today, so I'm trying to get this episode shot and everything before I get there. But anyway, I will definitely give you a shout out in the next episode. And in the meantime, if you're interested in joining the club, you can check out the link in the description. And for those of you interested in investing, check out WeBull, an amazing platform for buying and selling stocks, and now cryptocurrencies like Bitcoin, Dogecoin, and others. Open an account and get a free stock valued at up to $200, and fund your account and get another free stock valued at up to $1,600. Check out the link in the description and help the channel at the same time. Thank you. And don't forget about our merch store, which now has "Physics is the Law, Everything Else is a Recommendation," which is a quote by Elon Musk, as well as other t-shirts, mugs, tumblers, etc., etc. Check it out in the description. And finally, don't forget we are both Tesla and Amazon affiliates. If you check the link in the description, you can see how going shopping for a Tesla, a solar roof, a power wall, or anything on Amazon helps out the channel. And as always, feel free to ask me questions in the comments or at my email address, which is drknowitallknows@gmail.com. Till next time, bye-bye.